Today we got the missing tools we needed to fully disassemble this. The 5mm square drive came in, kind of an odd size here. And we're gonna just see if we can take these screws out with an impact driver. And you can. And if you look underneath, it's just an interference fit there. So that just deforms the metal in there. So I imagine that when we take the bottom one off as well, that is very tight. All right, got it. Okay, yeah, these are just standard, as standard as a square drive can be. But yeah, look, these will not come out now. This is the very definition of planned obsolescence right here. These shafts are non-removable. I have an arbor press. It's sitting here in the corner right now, kind of just waiting. And I think that even with an arbor press, we're going to have a hard time. And of course, even if we can move these with an arbor press, the aluminum being as tight as it is, scratching these shafts up. So this is a terrible implementation. Or alternatively, from Bantam's perspective, if you don't want the machine to last a long time and you like planned obsolescence, it's a great way of doing it. All they're doing here is they're just deforming the aluminum. When they screw this in, it's deforming this entryway, which is keeping the shaft from moving. So the summary on this is that the mechanicals in this machine, if one of these bearings breaks, you cannot replace it, period. It doesn't make any sense at all. But now we know that for sure. And yikes, that is a very, very interesting design decision. From a repairability standpoint, this is not repairable. If any of these bearings break anywhere in this machine, you can't fix it as a consumer. 0 out of 10 for the repairability on the mechanical structure of this device. All right, so because we can't take the Z stage off, which has the spindle in it, we can't remove these shafts, and so we can't actually take this off, and so it won't fit in our tester here. So this would be the correct way to test this motor. But unfortunately, we would have to somehow affix this entire device, because it doesn't disassemble, into this. And I haven't figured out a way to do it because these arms get in the way. I mean, this would have to be upside down, and it's 40 pounds, and so that doesn't work. So we're going to do a less scientifically valid, but equally representative test here, and I'll kind of point it out here. I have some labels here just for our reference. So what we're going to do is take a motor that we have tested on our correct test bed, and so we have its profile, and we're going to run this motor with the same PCB and the same reference motor, and we're going to use it to calibrate another motor here. And we're going to use that to also calibrate, this is just a rectifier here because this is obviously a 3-phase AC signal. And then we're also going to use that to calibrate this device here. And when I say calibrate, we're really getting a reference. So we're going to basically take a known device where we know at 3,000 RPM, this motor made 188 watts of power, just as an example. And at 2,000 RPM, it made, who knows, right? And that'll give us inaccurate information for the motor that we know the values of. And so we can actually say, okay, well, this motor we know was outputting 188 watts, and we measured 150 watts, and therefore we know there's 38 watts lost at 3,000 RPM under these very specific test conditions. And we'll do that for multiple RPMs. So we'll basically have a correction graph that we have to apply. We'll then use that correction graph to calibrate this motor. So it'll kind of be a second derivative of the actual correct way of using a Prony brake tester that I showed previously. These motors are coupled together with a belt. Now, to do the reference calibration, we're going to just do a 1-to-1 because both of these motors are rated for 3,000 RPM. But when we go to the Bantam machine, we're going to actually have to step that way down because I looked it up, and this is rated to 28,000 RPM. This motor is not going to be calibrated to that because it's only a 3,000 RPM motor. So we're going to basically do a big gear reducer. So we'll be able to drop this 28,000 down to below 3,000. So really we need to drop it down by 10 times. So we might have to use a sheave that's even smaller than what's on there now, just depending on how many teeth are on this guy. All right, so we've got our reference motor all figured out. Just full disclosure here, this was not the motor I showed in the previous video. I ended up using this motor instead of the smaller one that I had previously had. Nothing else has changed, but just conceptually we're using this motor as our reference. So it's now the motor that is calibrated to the rest of our equipment over there that we mentioned earlier. And the way we're going to hook this up is we've got this just goofy 100T sheave. I've never actually mounted this to a motor. It just looks crazy. And then we've got a 16T mounted here. So we'll reconnect the entire motor, and that way we're actually testing the at the spindle torque here. And I'm going to basically just mount this to the T-slot, and then we'll be able to move the T-slot to tension a belt. Now when it comes to the belts, this is the largest closed belt that I have, and it doesn't even fit around this 100T sheave. This is just goofy big. So what we're going to do is we're going to 3D print a belt here. Of course I could go buy, it's a 10-inch inner diameter that I need. The Markforged can print Kevlar. This is not an endorsement for the Markforged, but it does print Kevlar, so I'll say that about it. So we'll print a belt, see if it doesn't just fly apart on us. I've never printed a belt before, but the nylon they use is pretty flexible, and the Kevlar should be pretty flexible too. So we'll see, it might not work, it might be a total disaster, and we'll have to buy a belt. All right, here's our belt. I just drew it real fast here in Inventor. Came over into Eiger here. I had to make this belt 3 millimeters thick before Eiger would let me put Kevlar in it. And I am so confident this belt is not going to work that I've already purchased one online, but it won't be here for a couple days, so what the heck, we'll try this anyway. And if we go to internal view, you can see that we only have the one ring of Kevlar, and Eiger, of course, is defaulted to just having a few rings. We're gonna go ahead and just add a whole bunch more fiber here, and just go with the default settings here, and it's just slowly adding them. There you go. So we'll see if we can make this belt strong enough that it doesn't just totally fly apart. I'm worried it's going to be too thick at 3 millimeters, and it's just going to be too rigid, which is going to make the belt slip. All right, so we're printing the belt here, and it's just really thick. I don't think it's going to work, but hey, what the heck? Well, we might as well just keep going and see. All right, hot off the press. I don't think this is going to work, but we can try. Let's see. It's too thick. But yeah, that's pretty hard. The outside wall immediately comes off. Maybe we can just rip all of this nylon off now and just use the Kevlar. Yeah, glad I bought the belt, because I don't see this going anywhere. Well, we'll throw this in our pile of bad ideas and wait for that belt to arrive. All right, so through the power of waiting 2 days, we have our larger closed belts, and through the power of me buying 2 of them, I've got one hooked up here. So the signal basically is we have the power out here we're trying to measure. We're turning this belt. It's going into this motor, which we've calibrated. We've also calibrated this active rectifier here, and we've also calibrated this too. We have our calibration data to apply to this. So basically, as I spin this guy, you can see we start to develop a voltage here, and we're also counting the RPM. The RPM you see here is not the RPM of this motor, and it's not the RPM of that motor. It's actually the electrical RPM of this motor. So we've made a conversion chart here. This does overflow at about 26,000 RPM, just because of it's made for a different. The way I'm counting on it is made to do between about 0 and 7,000 values, so about 21,000. So we'll ignore that. We're not going to home because we're actually using the axes to hold our belt in place, and we're going to do M3 to start the motor, and that's just going to enable the motor. And then we're going to do a G1 G91Y plus 1, and actually we're going to do G0 to tension the belt. And so our belt is now nice and tensioned, and so what we'll do now is we're going to start the motor, and we're going to start it at a low speed. The speed seems to be a bit weird here. I don't completely understand how it's doing it, but what you can see right now is that we're generating about 8.7 volts at this first speed we've put in, and that's generating a 5,500 RPM value there, and we'll
see what that is. So 5500 is about 17,000 RPMs on this motor. So what I can do now is I can actually go in and place a load on this motor. So the reason we've calibrated this is I can now say place a 5 amp load. You can see when I do that, it starts to pull power. So the question really is then, what are we going to break first? Are we going to break this motor? Are we going to break the very tiny 0.5 millimeter by 10 millimeter, actually 9.5 millimeter belt inside? Are we going to burn out the motor controller that has no cooling whatsoever? Who knows, right? It's hard to tell, but we can tell for sure this is a closed loop motor. Okay, so yeah, we have 4,900, so we've gone from basically 15,000 RPM to, just about the same. So it is a closed loop controller, and we can actually now say put 10 amps of load on it. 10 amps is really hitting it pretty good there, but that is only a 31 watt load. But we're still maintaining our RPM pretty well. Let's go to 15 amps. And so at 15 amps, we've started to slow down a little bit. Still a closed loop controller. I'm going to drop back down to 5. I don't want to blow this up before I can gather some data. And we're going to just see here, sitting at a 26 watt load. The correction factor is not quite linear, so we can't just apply a scalar to it. But it's about 1.3. So if we multiply the power level by 1.3, that's about what it is. So that's about 35 watts. Keep in mind this is rated to 250 watts. So we're loading it at maybe 15% right now. Okay, so we've got our thermal camera here, and you can see the load we've placed on here. The motor is about 98 degrees. One of the things I wanted to point out is how poor their heat flow is. They're trying to exhaust a lot of heat through here, but it actually has to go through the motor body, and then an aluminum piece, and then there's another aluminum piece, and then it has to come back up through here, and all the heat has to conduct through this tiny little channel here on both sides, and then from there there's a connection here. However, this piece in the middle is a separate piece, and it's either touching one side, the other side, or no sides, which means the heat has to then go down. There's no thermal compound or anything on it. So at the end of the day, you're having to go through like 4 pieces of aluminum, this tiny little narrow channel here, and then you can maybe get to this heat sink. And you can really see that in the picture here. You can see how the heat is staying in that motor because it's not, the path is not very well done. There's no thermal compound, even with thermal compound, it's very small. So you can see the heat definitely builds up in the motor body itself. Now let's go back and look at the controller. And I know this is out of frame. Oh boy, our controller is really warm. Our controller is 115 degrees at a 15% load. So if I had to guess, then I'm going to say the controller is going to be what blows up first. And if it does catch on fire, we'll get there. But let's go into a higher RPM, and let's just first verify that we're getting to the 25,000 RPM value. Now, the values I enter here are kind of weird. They don't seem totally correlated to the actual RPM. So at this point, we're getting 8,600, which is about the 28,000 RPM value. And I'm going to go ahead and place the 5 amp load I had before. And you can see that we're maintaining 8,000 RPM. And so this is now 72 watts with a 1.3 correction factor. It's going to be maybe 85 watts. Here the motor is comfortable, 93. The motor controller back here is 125 degrees Fahrenheit. So remember, this motor controller has no fan, and it's actually wrapped in heat shrink. So that's probably going to be what dies first. So let's go to the full speed now, which is, ooh, I can smell belts. So we're now running at full speed. This is 108 watts. So that's going to be 135, 140 watts or so. And motor controller is very, very warm. 136, 142. Yeah, so 142 degrees on the motor controller. And we're still rocking around, actually in the mid 90s here. So let's go ahead and hit this up. We're going to need 10 amps. And And so unfortunately, that would be the rated output power would be 10 amps at 24 volts. And so we obviously were not able to hit that output power. We actually shorted out. The power supply has an overcurrent in it that's at about 400 watts. Get close. There we go. Okay, cool. That way at least... Okay, so we're tension now. What we're going to do is we're going to have to ramp up a little bit more slowly. And so we're going to set our load here to 1 amp. So we've got a 1 amp load now. And we're going to do the same thing. So we're going to do M3. And then we'll say S5000. See if this motor will start. Yep. And we'll go right up to that maximum value here. So once again, we have overflowed the counter here, which is okay. As soon as we start placing a load on this, that'll go away. So we're going to say 5 amps, and we'll say 7 amps. So that is 145 times 1.3, 145 times 1.3. That's 188 watts. I'm going to leave that there because that's actually the continuous power rating of the motor that I was showing you before. Its continuous rated power rating is 188, and that's basically quarter horsepower right there. So this is the quarter horsepower rating that this motor is rated for, and we'll just keep that there and check out our temperatures. So motor is actually not that hot. The spindle body is not that hot either, which makes me think. Obviously, some of the cooling of this is so that the spindle bearing heat can exhaust as well. What value do we need? To hit 250, we need 192 watts measured there. So we need another full amp. We're going to go to 9 amps. And so that's 179. We need 192. So actually, we're starting to peter out here. Let's try 9.5. And that's 186. So we still need more. So we're going to go all the way up to 10. And now we're hitting the 193. So it takes 10 amps to hit the 200, the quarter horsepower rating. That's currently what we're loading this at. And let's look at what it looks like here. Belt's pretty warm. The motor body's 95, so not bad. I imagine the motor controller itself is warm. Yeah, motor controller is 165 degrees right now. Actually, the connector we're pulling out of, our FETs are on fire. Our FETs are 190 degrees Fahrenheit. So I'm going to grab the camera over here. So this is one of the reasons you don't want to cut the high side of your channel. They're cutting the positive rail when they should be cutting the negative because it adds quite a bit of ESR having to have that second FET pair. So if you look here at the temperatures, you can see that the FET pair on this board is 188 degrees Fahrenheit. And that's basically what's controlling that motor controller. I wouldn't be surprised if these guys just totally exploded. Again, this is the rated power of this motor. They're not doing any current sensing. Yeah, we're definitely thermally running away. Let's check on the motor. The motor is about 115. So the motor's definitely warmed up with this constant load. We're still pushing the 191 watts, so certainly closed loop controller. What can I say? The motor controller actually has quite a bit of power, but it's like putting a big old V12, 6-liter engine in, a Honda Civic that can't even use that power because, this spindle is going, by the time it's using all the power, your steppers are going to have slip. So I'm actually really impressed with the closed loop off-the-shelf solution that they've designed. Once again, the part they've designed is the part that is just barely hanging on for life. Yeah, we've now hit 206 degrees Fahrenheit on our FET pair, and our FETs are just burning up. Our power supply fan is definitely on at this point. We're pushing it to its brink. Still rocking. The power has dropped a little bit, so we need to actually step up here. So we'll go to 10 point. 293. This is the rated power output of this device. And, ooh, something's happening. It definitely just tried to change speed on me there. Our FETs are at 217 degrees Fahrenheit, and yep, something's happened. Something about the motor is not happy. It's probably telling you, hey, I'm about to catch on fire. I imagine that's what that beeping means. I don't know if you can hear it. So let's see. Motor controller is 135 degrees. That's just as measured on the heat shrink tubing. And yeah, I'm pretty sure that's telling me that I've overheated. So let's see what we actually measure on the inside here. 156 degrees Fahrenheit on the, I took the heat shrink off here, and it's warm. So it's cooled off a little bit just because I've had the heat shrink here off. But yeah, it was definitely saying, hey, I'm on fire, I need to cool down. So I'm wondering if the motor controller itself it turned off, and then when the load came off, the power supply turned off. So, in summary, the Bantam's spindle was able to run for 5 minutes and 6 seconds at its full rated power output, which is 250 watts. So that is 106 times less time compared to this equally rated spindle. This is also a 250 watt spindle. Now the first failure modes were different. The first failure mode on this one is that after nearly 9 hours at its full continuous output, the belt broke off. And replacing the belt on this is simple. You just loosen these 4 bolts, and then you just slide the old belt's broken off, you just put a new belt on, and then you just retension that, and it's done. Now, on the other hand, this one here was an overheating failure. The first failure was that this overheated, and probably at the same time, these FETs were also getting pretty close. FETs don't like to operate at 190 plus degrees Fahrenheit, which is where these were running at. We've basically made a Ferrari engine, and we've put it in a Honda CRX because we don't have enough power with these steppers. And so if we try to actually force that much power into cutting chip load, we're going to lose steps immediately. The brushless DC motor that's running the spindle and its control system is probably the best part of this. In fact, it's certainly the best part of this machine. It's it's 100% off the shelf, and the parts that are actually failing, right? The FET stage itself, and then of course the motor controller here being wrapped in heat shrink. It's designed to be cool. If you look at the back, it actually has a cooling plate on it, so you're supposed to mount a heatsink to it. Okay. So here's our belt that's had about, I don't know, 5 minutes of its rated load spec on it. And you can see that the belt is falling apart here. This is one of the internal beads on it. And looking at it now, yeah, I don't think that, it is fiber reinforced, but that's not Kevlar. It's something. All right, so I just took the motor off, and look at all of the belt debris that's in here. This is all of the belt that has already shredded off of this motor. You can see there's actually a line of just belt residue. This belt is not going to last a whole lot longer. The belts are already shredding out of it. It's pretty bad. So we're going to go ahead and try and eject the spindle body out of here and see if they're even preloading this spindle. If they're not preloading it, then there's going to be a ton of run out from these angular contact bearings not being compressed. All right, so let's look at the bearing play on the spindle. What I have is I have this Starrett 10th indicator, so every number is 1 thou. I have it actually on the collet chuck itself and not on here, so we're not actually measuring run out. We're measuring the bearing play side to side here. There's a little bit of measurement of run out as well, just because we're not all the way up in the top there. But if I load this, you can see that that's 3 thou, 2.5 thou. And if I go the other way, so there's 4 thou right there. We're actually measuring the
preload on the bearings there, and it seems like we have about 4 thou of play. That's going to, of course, turn into a lot of radial issue as well. So if we were to put this same indicator down here, now we can't pull on the tool itself because we don't want to measure the tool flex. We're more interested in the bearing play. So we'll set that to 0 or thereabouts. And so what we'll do now is we'll actually come up here, and you can see that even with just finger pressure here, that translates to a lot of play as this spindle is hitting the cutting material. And that's just in one direction, is 3 thou. So we're talking runouts of, so there's 2.5 thou one direction, and there's 3.5, 4 thou in the other direction, and that's pretty mild force. So this spindle has a lot of what would equate to be run out, which certainly is chatter, but a lot of it is actually just the bearing in the two bearings in the spindle not being preloaded properly, or sufficiently, I guess is a better way of saying it. So to take this spindle off, we're gonna have to use this tiny little Allen wrench that came in the mail today. It's actually there. These things are super, super tiny, and there's no reason that you need to use an Allen wrench this small. I believe this is a 1/16 based on the metric stuff I had around previously. Let's see if that fits. It does. And you got to be real careful about not stripping these tiny bolts out. If they've used a thread locker on here, which it seems like they might have used a thread locker, it's possible we're not going to be able to take this spindle apart, at least non-destructively. But at this point, what's a little bit of destruction among friends here? I don't see anything about this that needs to stay intact. So yeah, we've already stripped this Allen wrench out. It's definitely the right size. So we're gonna go ahead and just heat this up. Just throw a ton of heat. We'll probably mess up the wiper on this bearing. If I were trying to preserve any of this, I would definitely cover that wiper with a metal shim, but I don't actually care. We've already done all the testing, and I don't see any reason why I would ever want to use or own this machine. See if we can get this guy to loosen. Make sure that tool is all the way in there. And wow, it's tight. There it goes. Okay. Let's see if that's gonna burn me. It's warm. It's not hot. Okay, cool. And so now this picks up. That is hot, however. And now this pulls out. We're gonna need to move this up, and we're gonna pull the spindle out. And here's more of our belt debris here. And so we pulled the spindle out, and it is just a tiny, there is no rotational inertia on this spindle. Yeah. So they're really relying on the motor. The bottom bearing is also a 7000-1 2RS bearing. Again, this orange wiper here it's called a W wiper, and they're not rated for direct exposure to chip and debris. You have to have some kind of shield over them, and this is what the bottom looks like. So this is in fact, this shaft is even hollow. Of course, the more you have around the circumference, the more mass you have around the circumference, or I guess put another way, the mass you have around the circumference is better than the mass on the inside. But still, at the same time, there's so little mass here. This is a spindle of a comparable size, actually. It's actually comparable there. But look at all the rotational inertia on this spindle. It's quite a huge difference. Also, the neck here is going to fail because it's a stress concentrator. So this has a unibody neck that's actually tapered down, so it never actually directly mates.
All right, so I did some digging around. This is the Bantam Tools spindle body here, and this is actually one that I had lying around. It's fairly similar. It's not quite the same. The attachment mechanism on the back is different, but you can see the shaft here. Actually, they have to do an reduced neck diameter there as part of the manufacturing process, and this becomes a huge stress concentrator. If you want to know how I know that, it's because the first spindle that I ever shipped would fail after about 6 months in the field, and we had a couple thousand of them in the field, and they started failing, and they break right here. So that's how I know that, and that's why you can't really use these spindles in a 1/4 horsepower setting. Anytime you crash the machine, it's going to immediately bend this head, and it's going to cause a bunch of run out, like measured in like 8 or 9 thou when you crash the tool. So this is not a good spindle body. This is kind of an off-the-shelf device. You can buy these from suppliers. So this is a very bad spindle design here. There's no mass, so there's no rotor inertia here, which means basically all of the torque and power has to be supplied by the actual electronics. Those closed loop feedback loops might have a 25 kilohertz response rate, but when you're chipping at 1,000 times per second at 28,000 RPM with a 2-flute mill, you don't have the response you need there, and so basically it's going to cause your spindle to stall out. We actually saw that indirectly when we were testing it before. When we stepped straight up to 10 amps, the supply turned off immediately because by the time the closed loop had responded, the spindle inertia was basically gone, and so it needed a whole bunch of inertia, which wasn't there, and then it caused a huge current surge. So yeah, this is a terrible spindle design. It is going to fail. It's not a question of if it fails, it's when. And when you crash it, it's going to make it fail even faster. So 0 points on the spindle design itself. The whole reason you use a Belleville spring is because it can deform quite a bit while putting a fairly linear and known force on there. If you instead just have pieces connecting in your tightening bolts or whatever, you could have 10 newtons of clamping force, or you could have a kilonewton of clamping force, all in the difference of maybe a 1/16 of a turn on your bolt. That's why you need to have a correctly coupled Belleville spring. The alternative is that you actually get a matched set of bearings, which this does not have. We talked about that before already. If you're going to have a matched set, they both need to be in the head of your spindle here. In this case, we just have the one bearing, so we know it's not a matched set. There's many other reasons why we know it's not a matched set. Also, this 7,000 bearing is a little bit small for a 1/4 horsepower spindle head. Typically, you'd have this spindle, for example, here, which is a comparable model, is a 7002, and it's a quite a bit larger bearing. It's also an angular contact bearing. So this is more appropriate bearing for this type of 1/4 horsepower application. So yeah, it's just interesting. If you look at the weight difference on these, the rotational inertia is a function of the circumference. How much mass do you have around the circumference mainly? The mass in the very center doesn't do anything, and the further you get out, the more useful that mass is. This weighs about 500 grams maybe. This is probably closer to 80, maybe 100 grams. I'd have to rock the scale out. I'm not going to do that, but it's pretty hefty. I mean, you can even just see it here. This is a 1/4 horsepower spindle head, and it has a 25.4, so that's 1 inch by, I can't quite get in there, but approximately 64 millimeter. This is a, what was this, 10 millimeters? Yeah, so quite a bit thinner, and pretty short as well. So, yikes. And so yeah, the way that you assemble this is you put this head in, you drop this nut on top, which is going to space away from your bearing, and then you put these incorrectly done Belleville springs on here, and then you throw this head on here like that, and now you're going to actually clamp it here, and you'll take your Allen wrench here, and you're going to basically, by tightening this, you are essentially going to preload
However, there's no limit on how far you can screw it. And so what they've done is they've actually placed 2 spacers here to control the actual preload to keep the spindle from binding. So I'm wondering if they're actually going in there and yeah, these are actually like precision shims. This one's like 1 thou thick and I'm having a hard time picking it up. But yeah, this is like maybe a 3 thou shim, and that one's closer to 5. So I think they're actually assembling this and then seeing when it binds or if it's not preloaded hard, because right now I can actually feel looseness in that spindle head. And so probably then they take this back off, and then they have figured out that they need these 2 washers to get the correct amount of feel. And preload is impossible to measure by feel. You could be off by an order of magnitude and not know it. So not a valid way to do preloading with the bearing. If you want to get a matched set of bearings, that is a computer controlled application. So yeah, now with this on like that, now the spindle feels, it at least feels stiff. And then of course this piece in the middle here is still going to rotate, which is why we have to take that little Allen wrench, which I've lost. I'm not even gonna, oh yeah, here it is, okay. And you have to actually set all of these screws here. So overall, even though the spindle was able to provide its rated power, there's some huge concerns on how long it can provide the power. And also, of course, the machine itself, the rigidity of the machine, and the lack of power in the steppers kind of make any saving grace of the spindle kind of a moot point, because it's not actually usable energy if your machine is just going to be sliding all over the place because it can't position its steppers correctly. So I think with that, I'm probably done testing the hardware on this machine. I have played around with the software on it as well, but I don't really care to learn the software on this because it is really bad, and 2 of the 3 applications crash the program. I will show you that, of course, but don't expect 5 videos on the software because there's no way I will ever use this machine for anything. It is terrible. I would throw it away if there weren't some useful parts on it. You know, getting like $20 worth of steppers out of it. Maybe I'll take up the hobby of quadcoptering and I can use the spindle motor controller since it's just a PWM controller. But honestly, otherwise, I give this machine a very low score. I don't have a scoring system, but you know, the icing on the cake is the fact that you can't even take these shafts out once they've been installed because they are deform inserted by these screws. Yeah, there were a lot of very interesting design decisions made on this, and a lot of them were probably incompetence, but something like this is I think willful planned obsolescence, and I just don't really want to support a company that rolls like that. So yeah, that's it for the hardware review. I'm not even sure I'm going to put this machine back together. I'm probably just going to strip the parts off of it that I find useful and be done with it. Yeah, this is a total dud, and I think it would need a complete redesign and then probably need to be branded under a different name before I would consider buying it again. This is an absolute do not buy. It's really bad. So what do we do with this machine then? I have a theory here. If you take some felt feet and you stick them on the bottom, here, there, and here, and put one right there as well, like that. And if you take it now and turn it over and open the lid, I think it might be a good trash can. Looks like I'll need to get some bigger bags, but it kind of works. I like the lid. You know, it'll cover all of the disgusting things that you put in it when you're done using them. Might as well recycle that.